Today's connected world is giving way to a future of smarter connections between smart cities, smart automobiles, smart homes, and smarter devices. ANSYS drives the innovators of smart systems and interconnected devices with the design tools they need to deploy successful products faster, cheaper, and more reliably. Major automakers are envisioning a world of self-driving cars. These self-driven cars will rely heavily on vehicle-to-vehicle and vehicle-to-infrastructure communications, advanced sensors, and will even provide a way to connect with your smart home. Smart homes are the future of residential technology, part of the Internet of Things revolution. Smart home technology will deliver and distribute services inside and outside the home using a suite of wirelessly connected devices. Cities are also getting smart, as wireless connectivity allows improved and novel services at reduced cost. Connected wireless technologies are likewise being integrated into modern aircraft. In all of these applications, sensor and communication systems must simultaneously operate within complex electromagnetic environments. The installation environment brings significant factors that impact the overall system performance. ANSYS Hfss SBR Plus is a new analysis tool for modeling installed antenna performance. Hfss SBR Plus, formerly Delcross Savant, works in tandem with Hfss, employing an advanced shooting and bouncing rays technique to model antenna interactions in regions spanning thousands of wavelengths. We'll now show how SBR Plus with Hfss can simulate antenna performance in each of these application areas. We begin with automotive radar. Driverless and traditional cars rely heavily on radar for safety systems, navigation, and driver assistance. Radar, optical, and acoustic sensor data are combined to construct a complete picture of obstacles surrounding the vehicle. Most vehicular radars use large aperture antennas to achieve high spatial resolution and support obstacle detection and identification algorithms. This is a virtual prototype of a 76 GHz slot array radar antenna. Hfss can readily simulate this and other array topologies, such as microstrip patches, at the millimeter wave band set aside for automotive sensor applications. The surface currents and radiation pattern predicted by Hfss illustrate the electromagnetic behavior and performance of the array in a freestanding configuration. The array will be part of a radar system installed on the front of an automobile. The surrounding metal and plastic will affect the shape, gain, polarization, and lobing structure of the radar beam. After the Hfss simulation of the array completes, we initiate the vehicle installation by invoking the Hfss data link to SBR Plus. The data link exports the array's 3D structure and field solver results to SBR Plus to drive its ray tracing solution for the vehicle interaction. Here we see the detailed current sources representation generated by SBR Plus after importing the Hfss predicted field distribution over a closely conforming box. Once we import the car CAD model into SBR Plus, we can easily place and orient the array on the bumper using point and click. This is the free space antenna pattern regenerated by SBR Plus after converting the Hfss near-field capture into current sources. It does not yet include the SBR Plus simulation, so the beam shape and side lobes exactly match those from the Hfss simulation of the freestanding array. Next, SBR Plus uses ray tracing to model the array interaction with the vehicle and predict the installed antenna pattern. Strong vehicle scattering causes pattern side lobes to rise and multiply. Main beam shift, shape distortion, gain loss, depolarization, and side lobe levels are all critical metrics in modeling the performance of the radar system. From your car, you can connect to your home's automation functions, such as adjusting the temperature and lighting. The smart home is another large and complex electromagnetic environment. SBR Plus accurately captures and quantifies the interactions between wireless devices in a home environment. Electromagnetic fields on large regions can be visualized, revealing areas of fading or blockage. SBR Plus also calculates antenna-to-antenna coupling, linking results from the Hfss antenna, component, and device simulations. SBR Plus characterizes signal power between devices across the smart home. Ambient electromagnetic noise must also be considered. Wireless devices can be overwhelmed by nearby sources of intentional and unintentional radiation, such as another device or a microwave oven. Whatever the radiation source, SBR Plus incorporates the critical role played by the surrounding environment in determining system behavior. From Wi-Fi to WiGig frequencies, where the home environment spans thousands of wavelengths, the powerful SBR Plus simulation technology is well suited to tackling the engineering challenges presented by burgeoning IoT applications. Here we model a streaming media player that connects your TV to the internet to obtain content from online services. Data throughput must be maintained to ensure high-definition picture quality. Throughput depends on receive power, noise power, and other factors. If the signal-to-noise ratio drops below a certain threshold, the system may compensate by switching to a lower data rate, reducing picture quality. In this scenario, the fields across a large grid are due to a wireless router. The grid represents possible TV locations. Field distribution on the grid depends upon the router's position, operating frequency, and the surrounding objects. The physical modeling in SBR Plus predicts the impact of TV and router positioning combined with environmental propagation effects of multipath, wall penetration, and even diffraction around obstacles. Antenna coupling simulations can even be expanded to electrically enormous environments, such as cities. Here, SBR Plus predicts the signal fading along a traffic route served by a fixed base station. Finally, we look at SBR Plus for aerospace applications. In this example, a vertically gimbaled reflector antenna is axially mounted for horizontal steering within a radome located above the rotor of an Apache helicopter. The reflector's feed horn is automatically generated from the Hfss antenna design toolkit. It is then solved in Hfss. The data link exports the conical horn feed into SBR Plus in a highly accurate near-field capture. SBR Plus completes the simulation of the standalone antenna by modeling the interaction of the feed with the parabolic reflector. Next, the semi-transparent radome and helicopter are included in the simulation. The installation significantly distorts the radiation and receiving pattern of the antenna, particularly outside the main beam. ANSYS Hfss and SBR Plus provide a complete antenna design flow, from individual antenna design to product integration to modeling antenna coupling and performance in the product environment. ANSYS provides the innovators of the connected world and smart systems with a complete design platform, spanning RF, electromagnetic, mechanical, fluid, and behavioral modeling. Thank you for watching this ANSYS presentation.